I appreciate you coming here to listen to my talk. Last time I was preparing this talk, I was almost in time, 18 minutes, so I will go a little bit faster than it should be. My name is Yuri, and I'm from Intel Corporation, Product Security Incident Response Team and Security Center of Excellence. And this talk is about vulnerabilities in the network drivers that can be exploited remotely, both remotely and locally. I will mostly speak about wireless examples, the examples in the wireless LAN drivers, but major results are applicable to any network drivers. So the agenda of my talk is as follows. First, I will describe the remote vulnerabilities in wireless LAN in wireless LAN case only. You heard from, well, it's this area was covered during last year quite extensively, but hopefully I will deliver some more interesting results, and we'll see that. So it will include wireless introduction to the wireless LAN frames format, then how to fuzz and how to construct your own simple beacon frame fuzzer. Then we'll discuss more advanced examples of vulnerabilities, remotely exploitable vulnerabilities in WLAN drivers, and briefly touch the environment that penetration tester of wireless LAN drivers should should have. Then we'll discuss a simple kernel mode payload on Windows for demonstration purposes. So basically, to demonstrate that the vulnerability is actually exploitable, it is often necessary to show the actual results of exploitation, and this payload can be used for such demo purposes. Then the vulnerabilities in the network drivers can be also local, so they can lead to local privilege escalation, and we'll discuss them as well. And finally, sorry, it's not the finally, but some specific types of local vulnerabilities in the network drivers can be exploited actually remotely by the attackers, and I will demonstrate that. We'll discuss an example of such vulnerability, how to exploit them, and how to identify them while penetration testing. And I'll show you the brief demo of exploiting remotely the local vulnerability. And finally, I will describe two examples of mitigated vulnerabilities in Intel Centrino WLAN drivers. The first example is remote code execution vulnerability, and the second is local vulnerability. And I'll conclude. So first of all, remote wireless LAN vulnerabilities. Let's discuss the format of the brief format of the WLAN frames. First of all, they can consist of a MAC header defined by the MACPHY specification, and you can see this header on the screen. It contains type and subtype information, for example, beacon subtype of management type frame. It contains source destination, access point, MAC addresses, BSSID, and some other information. The MAC header followed by the variable length frame body, also defined by the MACPHY specification. This is more interesting part of the frame for attackers. It contains some mandatory fixed parameters like capability info, authentication algorithm ID, etc. But it also contains a number of tagged information elements, such as SSID or supported traits. Tagged information element can be described by the following structure. It contains the ID of the information element, the length of the information element, and the contents of that element. So it is clearly the type length value structure. You can see the two examples of information elements that can be present in the wireless LAN frames, SSID and supported traits. So, why information elements is a nice way for an attacker to exploit WLAN driver? First of all, the length comes right before the information element data and is used in buffer processing. For example, the attacker can send unexpected length to trigger some kind of overflow. The maximum information element is 255 bytes, which is in most cases enough to contain some kernel mode payload. And a frame can have actually multiple information elements. So this gives an attacker even more space for the shellcode to place there. Also, drivers may accept and process unspecified information elements within the frame. Unspecified means that the MAC-PHY specification doesn't specify that this particular wireless frame has or should contain this information element. But it's not true for some of the drivers. Some of them may parse and accept and process the data in the unspecified information elements. And I will give you some example of that. So the example, which is very close to the example on the previous slide, but there is a difference. Where is the difference? The difference in the length parameter. The maximum length of supported traits element is 8 bytes and defined in NTDD NDs.h, but not every driver developer knows about it. Well, finally, all the driver developers will know about it. But so the length here is greater than the maximum length that is allowed for this information element, and this may cause problems. So, to construct your own very simple raw injection beacon fuzzer, we need to understand why I have chosen. I need to explain why I have chosen the beacon frames, beacon fuzzer. So beacons are good to exploit because they are processed by the driver even when not connected to any WLAN. They can be broadcasted and will be accepted by all the stations within the range. They don't need to. The attacker doesn't need to spoof BSSID or source MAC address. The attacker doesn't need a protocol. Basically, the beacons are not preceded by any frames. Well, in the protocol, so they don't have to. The attackers don't have to wait when target sends some request. They don't have to match the challenge response pairs and so on. So that's why the beacons are fairly easy to inject. And beacon frames support most of the general information elements such as SSID, supported traits, extended supported traits, and so on. So beacons are very rich on information elements. Basically, that gives the attacker a freedom to place, to find the vulnerability in processing different information elements. So the question is why beacons are used in most of the current exploits. To fuzz a length of a specific information element, supported traits, within the beacon frame, this code that you can see on the screen, well, basically, I don't need to explain this code in details because it's so simple that anyone can just look at and understand it in a couple of seconds. So to the left, it's the header and beacon management frame, fixed parameters, and some fake SSID element, followed by the ID tag of the supported traits element. And to the right is the code that generates supported traits contents from 0 to 255 bytes long, and the contents are increasing bytes. This is useful if, for example, in stack exploits, it's useful to identify quickly the distance between the buffer and instruction pointer and base pointer and so on. So it's fairly simple, and the full example I'm giving in the white paper. Basically, the white paper contains the much more information that than I will describe in the presentation. So for details, please go and read the white paper. All right, so that was very simple facts about the fuzzing and exploiting the and vulnerabilities in the wireless LAN drivers. But let's discuss more advanced remote vulnerabilities. First of all, we consider just beacon frame, but beacon frames may not actually contain any vulnerability. I mean, the driver may not have any vulnerability while processing beacon frames. So it is sometimes necessary to inject other types of frames. For example, association response frame. The attacker can exploit the driver while the station is connecting to WLAN or associating with access point by injecting the association response frame. So, but association response frame has actually some advantages. So, to inject a malformed beacon frame, it is roughly necessary to send thousands or even tens of thousands of beacons. To inject probe response, it is necessary to send hundreds or even thousands of probe response frames, and it's enough to send just 50 or 100 of association response frame to float the actual association response frame from the legitimate access point. And also injecting association response frames is less suspicious. Station is sending association request frame to an access point it's authenticated to, and the attacker sends malformed association response frames at rate roughly 10 per second. That's enough to flood legitimate response from access point. And this rate will rarely trigger the wireless IDS alert. So it is by exploiting the driver using association response frame, it is possible to collect all stations connecting to WLANs. For example, within this room or during a lunch in cafeteria. But association response frame has drawbacks. The station must be authenticated. Therefore, the attacker has smaller timing window. And the BSSID must match the MAC address of access point vulnerable station is associating with. In many cases, the SSID must also match. You can see the example, the screenshot of Wireshark screenshot of association response management frame. So, more advanced examples of vulnerabilities rather than examples of frames used to attack driver. First example, the driver may copy all the information element into the buffer on the stack or into the pool chunk. So in some cases, it's not enough to fuzz a specific certain information element, like we showed a couple of slides ago with the beacon supported traits information element fuzzer. Let's see at the example to the left. So there is a buffer there is a buffer that can contain up to 512 bytes. But McAfee specification specifies that frame body can be up to 2,312 bytes long, and this buffer is used to contain almost all the frame body, except the fixed parameters. So the driver, while parsing association response frame, copies the total contents of all the information elements within the frame into this buffer, except the headers. This it gives us it gives the attacker a way to so it triggers the vulnerability, whether it's a stack or a heap or pool vulnerability. So, summary: it's not enough to fuzz only information elements. Total frame size also matters, and this example demonstrates also that the space for placing the kernel mode shellcode in the frame is drastically increased. So you can place the payload larger than the 255 bytes in the frame, and this payload may get executed. Well, yes, there is an underflow actually in this example as well, but forget about this underflow for the moment. The second example: can the attacker place shellcode inside more than one information element? This example shows that it's possible to do. Vulnerability cannot be exploited in this example by a single information element. So, for example, it's not possible to exploit this code by sending malformed supported traits elements only, or rates element only, or extended support traits element only. But there is a stack buffer size is 16 bytes. It's the extended supported traits, and the code copies up to 16 bytes into this buffer. So it's okay. But what about the rates count internal variable of the AP-info internal structure that you can see to the right in the right top corner? Let supported traits be 17 bytes long, and extended supported traits contain up to 255 bytes. So both are copied in this example into the same buffer on the stack. 16 bytes are copied to the buffer while processing the supported traits element, but the rates count variable is set to 17. So when parsing the extended supported traits, this code will call the ndSmooth memory, and ndSmooth memory will copy minimum out of 16 and 16 minus rates count, which is -1. So guess what will happen with the driver. This example is given on this screenshot. You can see that the association, you can see the beacon frame, but containing supported traits element 17 bytes long, and the followed by extended supported traits element 255 bytes long, containing all A's. So important points from these two examples. In fact, let me go back to the example 2. There is a case tagged. The driver also processes SSID information elements and the information element, and there is also a vulnerability there. But this vulnerability and the example I'm describing in the white paper, it demonstrates that even the contents of the information element may trigger the vulnerability, not only the length of the information element, but a specific byte set at a specific position in a specific information element. So please refer to the white paper for that one more example. Important points. Multiple information elements are entangled. Vulnerability is triggered if both supported traits and it's an error. If both supported traits and extended supported traits are present, an attacker can place the payload within more than one information element. Maximum payload length is not limited by 255 bytes. So to be able to do penetration testing of wireless LAN drivers, the penetration tester needs to have a setup of the following systems. The injector system, having any wireless driver patched for injection. The backtrack final is, or the older auditor Linux Live City is very useful for penetration testing of wireless LAN drivers. And the system should have some kind of fuzzer. The tester can use Larcon, Ruby Larcon extensions in Metasploit 3.0, or the homebrew fuzzer that we described early. For row injection, using the fuzzer from the previous slides, it is necessary to configure wireless interface for row injection. MetaWi-Fi NG doesn't support anymore row def syscontrol. So to configure the wireless interface for row injection, you will need to execute the following config script. The sniffer system. Typically, Wireshark can be used for most of the purposes. And don't forget to listen on the same frequency, on the same channel, because sometimes it's really annoying when after a couple of minutes you understand that you're listening on a different channel than injecting. If you are testing in the environment that has lots of access points, then it is fairly easy to sync in the amount of beacons or probe responses or other frames sent by all those access points. So the Wireshark gives you a good way to filter the sniffed frames. So, for example, you can filter only beacons targeting specific destination address, or filter only association request and response management frames. And finally, you will need a system under investigation, which runs which has a target wireless adapter running target driver and some kind of kernel debugger, like Softice or Windows debugger. Two first systems can be combined into a single system if you have two wireless cards, for example, PCMCIA and USB card. So this is just brief introduction into the environment, and the other reference is given by David Maynard in the Beginner's Guide to Wireless Auditing. All right, so for the complete picture of remote exploitation of wireless LAN drivers, we will need to give a simple example of harmless kernel mode payload on Windows. Specifically on Windows, that can be used for demo purposes. So the harmless kernel mode payload. First, we need to find a trampoline address to redirect an execution to our shell code. The trampolines are the same as for user LAN shell codes, and in case of, for example, stack-based overflows, they are call ESP, jump ESP, push ESP read, or some other instructions. So it is fairly easy to search for these trampoline addresses in debugger, for example, in Softice, or in the using the s command, or in the Windows debugger. Using the same as command, actually, or any other tools like find jump 2 or find opcodes tools, fully available. For simplicity, I will use the hard-coded NTOS kernel addresses to resolve addresses dynamically. It's not in the shell code. It is necessary to one may use the vectors in the IDT table to get some address inside the NTOS kernel image and search lower memory addresses for MZ signature to resolve image base of NTOS kernel, and then parse its export tables. Then the shell code will have the function addresses, necessary native function addresses, but it's not the purpose of this presentation. So as Bokchak and Scape wrote in the paper, the kernel mode payload can be broken down into several stages: migration stage, stage 0 stage, the actual code being executed, like useful payload, and the recovery stage. So we don't use the stager stage because we don't need to port, for example, userland shellcode and execute it. It's the simple case of the payload. So the migration stage. First of all, the migration stage implies that the shellcode needs to drop IRQL to passive level because it will allow the exploited thread to be preempted by Windows Thread Scheduler, and this will avoid freezing the system upon recovery. Basically, there are lots of other disadvantages of running shellcode in dispatch level, so it is basically impossible to do so. So shellcode cannot, dispatch level cannot take the page faults. It cannot call most of the functions, for example, like synchronization functions like sleep and wait for single object and so on. So the first that shellcode, kernel mode shellcode does, it drops its IRQL level to passive level. Then this payload, for demo purposes, does something useful on the display stage. It resets the screen and displays the string owned on it using native boot video driver functions. Acquire display ownership, reset display, display string, and so on. It's fairly visible result of that the payload got executed during the exploitation of the wireless driver or any other driver. The recovery stage, it's a very important stage because the kernel mode payload doesn't want to. The attacker doesn't want to lose all the results after returning from the shellcode execution. There are a number of ways of smooth return from the kernel mode payload. One of the well-working results is given here. It's the payload can yield execution in a loop to other threads, so it will not freeze the system, and it doesn't impact performance too much, but the drawback is that the wireless will not work correctly because one of the wireless driver threads, exploited threads, will loop and will do nothing except printing owned string into the debugger and yielding execution. So most of the references, most of the information about the designing kernel mode payload on Windows can be taken from the Barnaby Jacks Step into the Ring Zero paper and Backcheck and Scapes paper. So did anyone already launch the payload I described? So okay, this is actually the result of that payload that I've just described in previous two slides. So the network drivers can be exploited not only remotely but also locally. There are a number of vulnerabilities that allow local privilege escalation and getting the kernel mode privileges to the attacker, to the user mode applications. Most of those vulnerabilities are in the device IO control local API. That is common to all the Windows drivers, and we'll describe briefly these kind of vulnerabilities. IO control codes is a common interface between mini port drivers and upper-level protocol drivers and user mode applications, which is more important to the attacker. On Windows, applications called device IO control function, Win API function, with the IO control code of an operation that mini port driver should perform. So therefore, the application, user mode application, can control device using this IO control interface. IO Manager Windows Executive passes major function device control down to the driver in response to this code received. The IO control defines a method used to transfer input data and to the driver and output data from the driver back to the application. The methods are buffered IO, direct IO, and neither IO. And actually, the vulnerabilities may be common to all of these data transfer methods, and but also may differ significantly from one method to another. So NDIS is a framework for drivers managing network cards. basically for network drivers. NDs defines object identifiers for each piece of configuration or statistics that an application can query or set to the driver. So, as a common communication path, device I/O control interface represents a common way to exploit kernel if a driver fails to correctly handle the I/O control request, or, for example, some of the object identifiers sent within this I/O control request. So, to exploit the I/O control codes, specifically network drivers, NDs drivers, an attacker should identify a correct object identifier that the driver fails to process correctly. In some cases, even the invalid object identifiers can also be exploited, and it is given in this example. So the driver copies unchecked contents of the input buffer into the internal buffer even before validating the object identifier, even before dispatching it to the query OID function. So the user mode application, malicious application, can send object any trash instead of object identifier, and this will trigger this vulnerability. So how to force the device I/O control API? First of all, we'll need to find a target device name. For example, enumerate objects in device object directory of object manager executive namespace. Use tools such as WinObjects by 4F, device tree, or WinObj. Network cards can also be enumerated using getAdapter in for WinAPI. Then the attacker, the fuzzer needs to generate I/O control codes. The fuzzer can use control code macro based on the device type, method access, and function fields. Device type is known from the device object. Each device type can have set of common I/O control codes, and these common I/O control codes can be simply hard-coded into the fuzzer, for example. But the network driver can also, or any other driver, device driver, can support any proprietary I/O control code, and it can fail processing them correctly as well. So the fuzzer needs to discover these I/O control codes as well. So the proprietary I/O control codes can be fairly easily generated, fairly cheaply generated. Method and access fields are almost fixed. They have 1, 2, or 3, sometimes very rarely 3 values. Function is within the range of 800. Below 800 is reserved by Microsoft, and between, for example, 810 in hex, so at most 16 private I/O controls, or maybe 128 I/O control codes. So it's not necessary to generate all the 4 gigs of I/O control codes. So then the fuzzer needs to, for NDs, for network drivers, the fuzzer needs to generate object identifiers. It can be used by sending OID gen supported list to get supported object identifiers. So basically, driver advertises the list of all object identifiers it supports. But the problem is that the driver again may support object identifiers, proprietary object identifiers that it doesn't advertise at all. So it will not return in response to the gen supported list request. So the fuzzer needs to generate them as well. So it is also fairly easy to do, actually. So the 2 most significant bytes are discovered using the gen supported list, and they are fixed across all the object identifiers supported by the drivers. And the least significant byte can be fuzzed within the between 0 and 255. So this is the automated method of discovering I/O control codes and object identifiers. But it is possible for attacker, for example, to identify all supported object identifiers and I/O control codes fairly easily by reverse engineering the binary of the driver. I will explain that in the next slide. OIDs are supported by NDs mini port drivers, by network drivers only. But we have any other, we have lots of other types of drivers. And for example, I will not cover this example here, but for example, for storage miniport drivers like SCSI drivers, the fuzzer needs to generate in the same fashion the SRBs instead of object identifiers. And finally, the fuzzer needs to vary the length of the input and output buffers, the sizes of the length of these buffers. To reduce this pace, the fuzzer may vary input and output buffer sizes around the size of the structure expected by the driver for a certain object identifier, and within the fixed set. 0 for -1. 4 it's the length of the object identifier. That's why some of the drivers, especially prior to NDS 5.1, they actually expect the length of the input buffer to be 4. Otherwise, they fail the request fairly early. So. I explained that it is possible to reverse engineer the binary of the driver and to identify the supported OIDs, because processing OIDs is typically done within the huge switch in the code, which is compiled into the jump tables. And it is this example of FIDE Pro screenshots gives a way to identify all general NDS 802.11 OIDs in the wireless LAN driver binary. I will jump over this slide and actually describing this in more details in the white paper. So we fuzzed mostly IO control codes, object identifiers, probably SRBs, and the lengths of the buffer. But we didn't fuzz the contents of the buffer. But actually, to have a, it's not a completely dumb fuzzing, but it's not also the very like smart fuzzing, because to make a fuzzing of device IO control API more smarter, it is not enough to fuzz only the sizes of the buffers. For each object identifier. Sometimes it is enough, but in many cases the fuzzer must be aware of the structures it is passing to the driver. Simple example, the driver may copy SSID length bytes from SSID into 32-byte long buffer in response to OID 802.11 SSID object identifier. If the fuzzer sends input buffer with the SSID less or equal than 32, then the overflow doesn't occur. Hence, the driver should be aware of that field, of that specific byte in the input buffer, which is SSID length. So that shows that the device IO control fuzzer needs to understand the structures it is passing in the IO control request for a certain object identifier. Most of these techniques we implemented in the proprietary IO control fuzzing tool, IO control BO driver security testing tool on Windows, and there's some information in the white paper for this tool. Couple of words about the state of the device and the driver. Device state matters. Examples. If the malicious application, for example, or a fuzzer sends OID 802.11 SSID, this is the request that wireless LAN mini port needs to return SSID of associated access point. So what if the station is not associated to this access point? The vulnerability is not triggered, even if it exists. OID 802.11 add key. Have station used in UWeb key. The vulnerability is encountered when a station is associated with some access point with web encryption. But it may not be triggered if there is an open system non-authentication encryption, or the access point supports WPA cipher suits, or the station is not connected at all again. OID 802.11 BSSID list. This object identifier is used to request the mini-port driver, wireless LAN driver, for the information about all BSSIDs detected by the station. Actually, the information not about just BSSIDs, MAC addresses, but the information about a whole bunch of information about all the WLANs discovered by the station. So the vulnerability, even if it exists, it may not be triggered if there are no wireless LANs in the range of station or the radio is off. Then the driver may support the proprietary MyDRV log current WLAN object identifier used by an application to obtain debug information about the associated access point. Again, what if the station is not associated with any access point? The vulnerability is not triggered. So the three major states defined by the original 802.11 specification based on the authenticated and associated states are not enough. The tester may consider the following additional states to fuzz the wireless LAN driver, and in each of the states, the vulnerability may be encountered. All right, so we have discussed the vulnerabilities in the device IO control API, which lead to local privilege escalation. And it's currently believed that they lead to local exploits only. But it's not true, and I will show you why it is so. So the next section covers remote exploitation of these IO control vulnerabilities. So local or remote. IO control vulnerabilities are less severe than remote because they are exploited by local user land exploit code. This is wrong, because IO controls are used to curate driver for information that WLAN driver receives mostly from the frames, from the outside. For example, detected BSSIDs, current SSID array supported by the associated access point, WPA information, and so on. So what will happen if the local IO control vulnerability occurs when returning this particular information? The vulnerability depends on the data supplied by the attacker remotely, and it can be exploited remotely. But an attacker needs to have a local agent that will send vulnerable IO control request with the vulnerable object identifier. It's a disadvantage for the attacker, so it still makes the vulnerability local because it should have a local code. It's not true. Any network management application, for example, wireless management application that you have on your laptops, or even a protocol driver, periodically queries ND's miniport driver for information sending different OIDs. So basically all supported object identifiers will be requested at some point of time, and some of them, especially those that I described on previous slide, are requested quite oftenly. These IO control vulnerabilities can be exploited remotely even after radio is off. So let's imagine that the attacker injected remotely some exploit code, and then the user turned off the wireless, and then the network management application requested for send an IO control request for vulnerable object identifier that contains a vulnerability. So the exploit code within the frames may get executed. The example of such vulnerability. You can see the code that processes the request for active BSSID info object identifier. It's a proprietary object identifier. So ND's miniport supports this proprietary OID used by management applications to query information about associated WLAN. The driver responds to this OID, returning the information stored in the internal connection structure, supplied remotely within beacon and probe response frames. When handling this object identifier, the driver copies SSID of associated AP access point from internal connection structure into a stack buffer without checking the size of SSID. So it gives us a two-step exploitation. First step, inject malformed frames, wireless frames containing the payload remotely. For example, the access point sends its information, including SSID-free Wi-Fi for all. And then some attacker system injects some malicious shellcode inside the SSID element. The wireless driver stores this information in internal structure, connection structure, and then some management application queries for a vulnerable object identifier BSSID list in this case. Depending on the data the driver received from these two stations. So it requests for this OID, and this driver tries to return this data, free Wi-Fi for all, and this weird SSID. So it allows attacker to exploit the driver remotely, even having the local IO control vulnerability. So how to identify them? First of all, to identify the IO control vulnerabilities that are remote, actually, we need to inspect registers and memory pointed to by these registers in the crash dump caused by the device IO control request for contents of received wireless frames. How to do it automatically? I don't know. I haven't managed to implement it yet. So I do it only manually. That's a challenge. So, and to increase the likelihood of encountering this type of vulnerability, the penetration tester needs to fuzz IO control codes along with injecting malformed wireless frames. This will give this will increase the likelihood that the vulnerability actually can be triggered during the fuzzing process. So I'll show you the brief demo. I will show you how to exploit local IO control vulnerability using malformed beacon frame, and I have modified old version of the Intel W29 and N51.sysWLAN driver. I introduced a demo vulnerability we discussed a couple of slides ago, and I used existing BSSID list object identifier instead of proprietary active BSSID info because well, to demonstrate that an attacker doesn't need a local agent to trigger the vulnerability. Let me open. Oops. Sorry about that. I'm not a good editor, video editor, so I apologize for a bad quality of sound and video. Oh, it seems I'm a really bad editor. All right, let's continue the presentation, and I will try to figure out what's happening with my demo that worked 5 minutes ago. After the, if we have time, after the presentation. All right, so I will briefly discuss two examples of vulnerabilities we mitigated in Intel Centrino wireless LAN drivers some time ago. The first example is the remote code execution exploit that we analyzed and created and demonstrated before previous Black Hat USA conference. The description of that exploit is when station was connecting to wireless LAN network, the exploit injected association response frames. I used 40 to 300 frames depending on different conditions, depending on the surrounding access points. In response to association request frame with the legitimate access point, the exploit used unspecified oversized SSID element within the association response frame. The BSSID had to match access point's MAC address, and the station had to be authenticated, for example, to the open system authentication access point that was actually used. So let's let exploit inject some nopes within the SSID element, and this triggered the bug check driver IRQL not less or equal, and we see that the contents of instruction pointer and base pointer were overwritten by the data specified by the exploit. But then let's try to substitute the fake payload with the demo payload that we discussed earlier during the presentation and inject it. This what happened in the result of using that exploit, and actually the exploit was more complicated than just injecting this demo payload due to many reasons. But I will not discuss them here. So this is the result of exploitation of Intel Centrino, old version of Intel Centrino driver that we mitigated and released an advisory before the Black Hat. I mean previous Black Hat. And the local I/O control vulnerability example. I'm using the proprietary I/O control fuzzer here to send the BSSID list object identifier. In response to this BSSID list object identifier, the wireless LAN driver should return information about the all detected WLANs in an array of ND's WLAN BSSIDX structures. The I/O control fuzzer is configured to allocate output buffer of a maximum size so that it doesn't crash and continue testing in case of if driver corrupts heap chunk. It may happen. So after sending this I/O control request with this object identifier, with the length of the output buffer between 12 and 127 bytes, the W29 and 51.sys returned 128 bytes of arbitrary kernel pool. So the user mode application at least can observe kernel pool contents, which isn't good, but not the end goal of the exploitation. If we turn off the option of allocating maximum buffer size and will allocate output buffer of exact size, for example 12 bytes for I/O control request, the driver writes 128 bytes into the 12-byte user land buffer and corrupts heap chunk. So the I/O control fuzzer ends up in OLI. This is the result of crashing the I/O control fuzzer by the driver. But again, it's not the end goal of exploiting the driver, right? The corrupting user mode buffer. So by changing a little bit, changing the state of the driver was accessing addresses outside of its pool allocation and crashed. So I'm continuing discussing this vulnerability in the white paper. So to conclude, the summary of this presentation. Although we focused on the wireless LAN driver examples, any wireless device driver is subject to remote exploitation. The longer the range of the radio technology, more attractive exploitation is. The exploits targeting such nationwide technologies as WWAN, 3G, WiMAX can be really bad for us because they are global and nationwide. So imagine that we can send the same demo payload exploit to the Los Angeles for the moment. Vulnerabilities in the device I/O control API can exist in any device driver and is a generic way to exploit kernel. For example, in network drivers, fuzzing ND's OIDs, object identifiers, covers all ND's mini-port drivers, WLAN, WWAN, WiMAX, Ethernet, Bluetooth, RDA, and so on. And the last is that local I/O control vulnerabilities may lead to remote exploits. So we need to they are as dangerous as any other remotely exploitable vulnerability. So as a call to action, blue screens in network drivers are not just functional bugs. We need to analyze every crash dump for a potential security vulnerability. We need to use available tools like on Windows Driver Verifier and NDIS Test for Windows drivers. We need to fuzz remote and local driver interfaces. We need to integrate automated automated static source code scanning into the development process, for example with Prefuzz or any other software static code scanner, and we need to do manual source code analysis. And we also, the drivers, need to leverage the available compiled-in protections like stack canaries and so on. As a final remark, I would like to acknowledge Nathan Bixler from Intel Corporation, and you see the contacts. You can contact us regarding any vulnerability exploit or any information about Intel products. All right, this is the final slides. I appreciate your attention, and I still have 10 minutes, I think. Wow. So let me try to launch this demo. Hi everyone. Oops. Thank you. So it is working with the on my screen. For watching this video. Oh, thanks. This demo is about vulnerabilities that exist in network drivers while processing device IO control requests. It is currently believed that these vulnerabilities may lead to only local privilege escalation exploits. I will show you that it's not always true, and they can be exploited remotely. I will use three systems during this demo. This one is a sniffer to watch in Wireshark injected frames. It is listening on the channel 6. This laptop is a Tigers system. It runs PuckTrack Final, and it has a wireless interface configured for raw injection. It also has a exploit code that will send many malformed beacon frames with oversized SSID elements. This system is the target system. It has Intel Pro Wireless 2200BG network adapter with old version of W29N51.sys driver. I have modified this driver to introduce the vulnerability that we are discussing during my presentation, and this system will be exploited remotely. Again, the vulnerability I will exploit is fake and exists only on this laptop.
The wireless is on and the driver is receiving some frames. I will run IO control fuzzer to show that in the absence of specifically crafted wireless frames, the driver doesn't crash after receiving a request for BSSID list object identifier. Let's first run IO control BO utility to discover device name of target device. It's Intel Pro Wireless 2200BG network connection. Let's run our fuzzer in NDIS mode. against our device. We'll send object identifier 0D010217 and buffers large enough to contain information about all discovered wireless networks. Let's say 10,000 bytes filled with small a's. And we'll log results into the log file, including buffers in verbose mode. Let's run it. Alright, it's finished fuzzing. Okay, we see the fuzzer sent IO control and disk query selected stats and requested for BSSID list object identifier. Here's the contents of the input buffer before request filled with small a's, and the output buffer before request. And then we received the response from the driver. You can see the contents of the output buffer after the request. It contains information about all discovered BSSIDs. You can see the SSID of discovered LANs, guest, default, and so on. So the driver returned 9,000 bytes correctly and didn't crash.
Let's inject some malformed frames. We'll use this laptop and we'll inject a bunch of malformed beacon frames containing SSID elements filled with all A's. The total size of each malformed frame is 70 bytes. And we'll see what we got on the sniffer system. Some amount of beacon frames. We filter by the destination address. Alright, so this is the SSID element consisting of all A's, which is 41 hex. So we're receiving some frames. I turned off wireless so that we did not get any crash while describing the injection and sniffing. But now I'm turning wireless on. This will trigger the scan for the available wireless networks, and the wireless management application, user mode application, will request the WLAN driver for discovered networks and will send object identifier BSSID list, which contains a vulnerability, and we'll see this. Alright, we got the blue screen, driver IRQL not less or equal, and it's we clearly see that the stop has parameters that are sent within the malformed frames or injected by the attacker. So let's dump the memory. Okay, we've finished dumping memory. Let's reboot this laptop.
Let's open this crash dump in Windows Debugger. Here we go. Take a look at trap frame contents. Both instruction pointer and base pointer registers were overwritten with the data we injected within malformed beacon frames. Let's inspect call stack. It shows that default occurred in miniport query information function. This is required for all ND's miniport drivers function and is used by NDs to query miniport for object identifiers. It was called with OID G010217, which is BSSID list. We learned two things from this dump. First, the vulnerability depends on the data we injected within malformed wireless frames remotely. And the second is that the vulnerability occurred in the functionality processing local request for BSSID list object identifier. It's exactly where we introduced our fake vulnerability.
We have just seen that local vulnerabilities in the device I/O control interface of network drivers are not always local and can be exploited remotely by the attackers. That's why they are as dangerous as any other remotely exploitable vulnerability. Thank you very much for still listening to this demo, and we'll see you in Vegas. I apologize for the bad quality of the video and sound, and thank you. I appreciate that you're still listening to my talk. Thank you very much. Any questions? We have 5 minutes. The question was, what's the best way to detect these before the crashing the system, these kind of vulnerabilities. So basically, when you trying to discover the vulnerability in the remote interface, you will most likely crash the system. So let's run that in the VMware workstation, or so you cannot you don't need to reboot each time and your system. The local vulnerabilities are not necessarily crash the systems. So the local vulnerabilities can corrupt the user mode buffers, and that indicates that the driver does not process correctly the buffers, but it doesn't crash the driver. So if you change the state of the driver, some specific condition, then the driver may crash. With the remotely exploitable local vulnerabilities, it typically crash the driver and the system. So we can use static source code analysis to identify them without crashing any driver. But the fuzzing of kernel mode implies that you will crash something. Yes, you may install the wireless IDS that will trigger some kind of alerts while observing malformed frames. For example, filled with NOP/SLAD or some other heuristics. So you can identify those kind of attacks and prevent from them, actually. It doesn't depend on the frame type, subtype, or the information element. You can the wireless IPS should be able to prevent exploits sent within any wireless frame. So it's not depending on the SSID or beacon frame. Which one?
It seemed as though the fuzzer that you had was specifically targeted to like fields, and if you were to just look at it from a pure black box approach, like you have a bunch of conditions that bound it, like you have the ID, you have the driver has to be in a certain state, so you have all these
Well, this vulnerability wasn't found. I introduced it myself. It's a fake vulnerability for this demo purpose.
Oh, okay, so there was
Yeah, I knew where the vulnerability is, how to exploit it, and I exploited it using the exploit code. It's not the fuzzer, actually. It's just an exploit code.
have you found vulnerabilities like this in a while?
Well, they may be found. All the examples I demonstrated in this demo are based on real code. Not the real code, but based on the on real vulnerabilities we encountered in the past. Yes, exactly. So with the question was if I'm waiting for the association request to respond 40 to send 40 association response frames. That is true. The attacker, to inject the payload within the association response frame, the attacker needs to wait until the user connects to WLAN and sends association request, and then the attacker injects. The attacker can inject 10 association response per second. It may not be 40. It may be an hour of injecting and collecting all the stations connecting to the wireless LAN frames. 10 per second, very slow, very low rate. So to exploit, as the first example of remote code execution in Intel Neutrino, I used 40 to 300 in response to legitimate association request.
I had two questions. The first one, can you bring up your email address again? And the second part, does that have any impact on being successful?
Yes, of course, DEP has impact, and it complicates exploits, but it doesn't prevent actually. Yes, that is true. Almost any. It can prevent specific exploits. The stack, the canary protection can prevent specific exploit. Any other protection mechanism can prevent specific exploit, but it doesn't prevent all the exploits. In these examples that I showed, for example, the DEP was turned off. So I just don't need to. I just didn't need to bypass it, and I'm describing this in the white paper. How to turn it off and so on. And the second question was my email address. Oops, excuse me. We have some references actually. So yuri.buligin@intel.com. It's not important for this presentation. For this presentation, it's just a demo of what can happen, and you see that if they do exist, then it's possible to exploit them remotely. I have not personally researched the smartphones, these exploits on smartphones, but as was telling during the presentation, most of these vulnerabilities are applicable to different types of network drivers. For example, 3G. 3G are on smartphones. So you can exploit smartphone 3G WLAN driver on a smartphone. Thank you very much.